A couple of weeks ago, I made a video of a Hello World example of artificial intelligence. The response was quite positive, which inspired me to create another Hello World example in the field of AI. A Hello World example of supervised learning in artificial intelligence using multilayer perceptron and backpropagation in C++. This new video builds on the previous one, serving as an extension to further explore the concept. In this video, I focus mainly on presenting examples in C++, but exclude CUDA for now, as including it would make the video too long. I plan to make a follow-up video demonstrating the same examples in CUDA after I return from my travel. To begin, let's have a brief review of Perceptron, which is the simplest artificial neural network and is a supervised learning algorithm. This diagram shows a simple perceptron. It has inputs x1, x2, blah, blah, up to xm, and x0 is 1, okay, as w0 is the bias, okay, and so each input has a corresponding weight. So we calculate the product of each input to the corresponding weight and sum them over, okay, as shown in here, okay. And then we add the bias, okay, and put this into an activation function to get a predicted output. Okay. So this G is an activation function, which could be a step function. Okay. And learning in the perceptron is to calculate this y hat, okay, by this formula. Okay, and here we simplify it by making W0 to be the bias and X0 to be 1. Okay, so this becomes the dot product of the weight vector and the input vector X. Okay, and we update the weights according to the error between the predicted output y hat and the target output or desired output. Okay. We multiply this error, okay, by a small constant, okay, eta, which is called the learning weight, okay, and multiply this by the input. Then this will be our delta wi. Okay. So update the weight by adding this delta wi to wi. Okay. And so this is a simple perceptron and how it works. And we discussed that this perceptron can only learn linearly separable patterns, like AND gates or OR gates. Linearly separable means we can draw a straight line to separate the data into different types. Like here, the white represents a 1, black represents a 0. We can draw a straight line to separate the white circle from the black circle. Okay. The same for OR gate. We can draw a straight line here to separate the black from white. Okay. But for exclusive OR gate, we cannot draw a straight line to do that. So that means the perceptron cannot learn for the patterns of exclusive OR gate. Okay. To do that, to learn the patterns for exclusive OR, we need to use a multilayer perceptron, MLP. And an MLP is able to distinguish data. They are not linearly separable. Okay, this is the diagram of a simple multi-layer perceptron. It has say an input layer with 3 inputs, x1, x2, x3, and a hidden layer. Okay, each of this node is a neuron. Okay, and an output layer, say 2 neurons. Okay. And we have ways connected from the neurons of one layer to another layer. Okay, so we have weight. Okay. So an MLP works in this way. It is, of course, a kind of supervised learning. Okay, the general idea is that we feed the MLP an input pattern X. Okay, as shown here, say X1 up to say Xn. Okay, this X is from a training set. Okay, and then MLP. Okay, this MLP, which consists of an input layer, hidden layer, output layer, will generate an output pattern. Okay, so we can call it Y. Okay, consists of Y1 to say YK. Okay, then we compare this Y, the output pattern generated by this MLP, with what we want, with the target YD. Okay, that's the target output. Okay. So usually we have an error. Okay. And we send this error back to adjust the ways connected the neurons between layers. Okay. So that in the next iteration, the Y and YD will be closer, okay, or the output generated by the MLP will be closer to what we want. Okay. We repeat this with another input pattern X from the training set, and we could train that many times so that the error becomes smaller and smaller. Yeah, to do this, we need an error function. An error function represents the difference between the target output and desired output, and the predicted output over a set of inputs. Okay. And a popular way to consider the error is to use the mean squared error, MSE, as shown in this formula. Okay, E is equal to 1 over 2k, sum from 1 to k, YDI, the desired output, minus YI square. We sum over this. Okay. And if we want to adjust the weight so that E decreases and eventually get to the minima. Okay. A common technique that people use to decrease the error function is called gradient descent. So basically, in this method, we adjust the weight so that E decreases along the gradient. Okay, like what this diagram shows. Okay, suppose this is the error. Okay, and this SS represents a W, one of the Wij, and then when we change the Wij, the error could change. Okay, and we wanted to adjust the Wij, okay, so that the error would decrease along the gradient. Okay, and the gradient of this curve is given by the derivative of the error with respect to the Wij here, okay, or partial E, partial Wij. Okay. So this method will lead us to the minima, okay, for many cases. Okay. But for some special cases, if we have say a special curve, the curve that goes down here and then goes up and then goes down. Okay. then we have a local minima, then we may be trapped in local minima, okay, and may not be able to get to this point. Okay. But here we don't consider those complicated cases. We consider a very simple example that won't have any local minima. Okay. And so this is the formula that we need to adjust the weights. Okay, delta Wij is equal to a constant times the gradient. Okay, partial E, partial Wij. Okay. Starting from this, okay, after performing a series of straightforward mathematical derivations, okay, we can arrive at the following algorithm that trains an NLP. Okay. So this is the Multilayer Perceptron MLP with back propagation algorithm. Okay. It works as follows. Okay. Now here are the notations. The inputs are x1, x2, blah, blah, all the way to xn. Okay, like this diagram shows x1 to xn. Okay. This is the inputs. Okay. And then we have the hidden nodes, h1, h2 to hm, as shown here. So each of this node is a neuron. Okay, so this is input neuron, hidden neuron, and this is the output neuron. Okay. And each neuron has a value. Okay. And then the outputs y1, y2 up to yk. So here y1 up to yk. Okay. And the two neurons between two layers, okay, are connected by ways. Okay, so this from x1 to x1 we have the weight w11. Okay, and then x1 to y1 we have w11 also, but to distinguish from this weight we can add another index, say 2 to it. Okay. And also we need an activation function. Okay. And the activation function here, we need a continuous function so that we can find the derivative. Okay, instead a step function. And we use a sigmoid function, which is given by this formula. It is 1 over 1 plus e to the power negative c. And the derivative of sigma, okay, sigma dash c is equal to Israel sigma c times 1 minus Israel sigma c. Okay. So from this formula, you can see that when c goes to infinity, this term is 0, e to the power negative infinity is 0, so we get 1. So that means this approaches 1, okay, as z increases. Okay. And on the other hand, when z is negative, okay, goes to negative infinity, then this is infinity. So 1 over infinity, we get a 0. So on this end, we get a 0. Okay. And the derivative of sigma function, okay, is given by this curve. Okay. So it goes to 0 at both ends. It's symmetric. And in our simple MLP, the structure consists of 3 layers. Only the input layer, hidden layer, output layer. Okay. So in more complicated cases, you can have more than 1 output layer. But here we just consider something simple, 1 output layer. Okay. And with the ways connecting 2 neurons. Okay. So Wij denote the weight from the input xi, okay, to hidden node xj, okay, like this, 1 to 2. So this will be w12, okay, and WJL represent the weight from HJ, okay, HJ to YL, okay, to YL, okay. And to distinguish this weight from this weight, we will add another index, O, to denote the output, okay. So this without the O, then it is for input weights, okay. Otherwise, it is hidden to output weights, okay. Or in this diagram, they use the index 1 and 2 to distinguish, okay, the two weight sets. Now in the algorithm, again, involved forward propagation. In the forward propagation, we compute the output of the network from the inputs, okay, that involve several steps. Okay. In step 1, we compute hidden layer activations. Okay. So each neuron HJ computes this sum from 0 to n wij xi. So this gives AJ for a particular neuron. So for this neuron, for example, we need to sum over say the product of say this x value with the weight, okay, and then this with the weight to this neuron, right? Sum over all this, okay, and so this we give a value, say AJ for each neuron, okay, and we put this AJ into the activation function G, okay, to get the value HJ, okay. So G is the activation function, okay, and we use sigma here. G is sigma, okay, the activation function 1 over 1 plus C to 1 minus C, okay. So that's our G. And in our notation, WOJ is the bias, and X0 is 1. Okay. And in step 2, we compute output layer activations. Okay. So each output node YL computes the weighted sum of hidden layer activations and apply the activation function. So each of these nodes will compute say this H value, HJ value times the weight. Okay, we sum it over, so we get to this value. Okay. So we get the CL again to distinguish this weight from this weight. We add an O here, denoting output. Okay. So we sum over J here. J, so basically this means from the hidden layer to the output layer L. Okay, so the CL. Okay. So for a particular output, okay, L equals 1 to K. Okay, and J is 1 to M. Okay. And again we put this value CL into the activation function, okay, G, to get the output, the predicted output YL. Okay. And again, in our calculation, W0LO is the bias, and we set XO to be X0 to be 1. Okay. So now we have the YL calculated. Okay, all this were calculated. Then we need to do the back propagation. Okay. In this process, for each output neuron YL, we calculate the error. EL is basically the difference between the desired output and output from the NLP. Okay. And we need to calculate the gradient of the output error. Okay. So it's the delta L, okay, that's equal to EL from here times G dash. CL. G dash is the derivative of G, or the gradient. Okay, so this partial G, partial CL, so this given by this formula. Okay, because we choose our activation function to be a sigma function. Okay. Then we update the this delta L. Okay. Then we calculate the hidden layer gradient error using this formula, delta J sum over L equals 1 to K. This delta L is from here. Okay, for each output neuron, we get delta L. Now we need to sum over this. Sum over this. Okay, and also times this to the weight. Okay, WJL. Okay, output value. Okay, and then we sum from L equals 1 to K. We do that over all the outputs. Okay, and times this which is the derivative of the activation function with the argument AJ. Okay, AJ is here. Okay, so that's the formula that we use. Okay, so after we got delta L, delta J, then we can update the weights. So we adjust the weights from hidden to output layer. Okay, so that's the WJLO. Okay, using this formula. So this is the delta WJL. Okay, basically it is the eta, the learning rate, times delta L times the hidden neuron value. Okay, HJ. Okay. And we also adjust the weights from input to hidden layer. Okay, so here we need to add the weight Wij to this eta times delta J times Xi. Okay, so these are the formulas that we need to use to do the update. Okay, and there's the backpropagation. So we iterate this, okay, for a number of times. Then the error will get smaller and smaller. Okay. Now to illustrate this algorithm, or to implement this algorithm, we consider a very simple example. Okay, exclusive OR. Okay, remember that exclusive OR, okay, cannot be learned or trained by a simple perceptron. Okay, as the data cannot be separated by a straight line. Okay. So this is the exclusive OR gate. Okay, suppose we have two inputs, x1, x2, and this is the output, the desired output. 0 exclusive OR 0 is 0. Basically, exclusive OR is a mod 2 addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, mod 2 is 0. Okay, so this exclusive OR. And this is the implementation of an MLP to train an exclusive OR gate. Okay. Let's copy this program and see, go through it and see how it works. We copy this and paste this into a file. this is the program that we have. Now let's save this. And before the explanation, let's try compile it and execute it. Okay, so you can see that we get what we want. Okay, the results of exclusive OR. Okay, and these are the actual values. Okay, and we classify them to be 0 or 1. Okay, now let's go through this first. Now, this is a strict implementation of the formulas that we just discussed. Okay. So we have N1, the number of inputs plus bias. So there's 3. M1, okay, there's the number of hidden nodes plus bias. Okay, M, okay, same M here. M1, yeah, this M plus 1, okay, and K is 1, the number of outputs, okay, and num samples is 4, okay, so 4 sets of inputs, 1, 2, 3, 4, okay. So these are the inputs for testing the, for training the data. So this 1, 0, 0, so that means x0 is 1, x0 is the bias, okay. X1 is 0, x2 is is 0, okay. Let's change this. This should be 0, okay. And 0, 1, okay, so 0, 1, 1, 0, 1, 0, 1, 1, okay. And x0 is always 1, okay. And the corresponding desired outputs, we call it labels here, okay, is 0, 1, 1, 0. So that means the output for this is 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is 0, okay, the target outputs. Okay. And these are the random ways from input to the hidden layer, okay, N1, okay, M1, okay, to the hidden layer, okay, there's some random ways. And WO is from hidden to output, okay? Hidden to output, okay, these ways, okay? So these are some random values, okay? And this is a simple class that implements the formulas. So we have this AXYZ eta, okay, the same as the notations we discussed here. The A is this A, okay, and the H, okay, is this H, okay. The Y is the output, okay. The Y with percent here, okay. Z is the Z here, okay. And here actually K equals 1, okay. We only have one output. And so to begin, we have a constructor. We pass in the learning rate. We set eta to be the learning rate, and x0 is always 1. It is for the bias. Okay. And this g is the sigmoid function. Okay, 1 over 1 plus exponent minus x. Okay. The one that we discussed here, okay. And this is the GD, the derivative of the sigmoid function, okay, sigma dash, okay, equals sigma times 1 minus sigma. Okay, so S is the sigma. Okay, so it is S times 1 minus S. Now if you pass in the parameter, there's already the value of the sigma function. This means the S. Then this could be omitted. Okay, but for clarity, we do it this way. Okay, even though it takes a longer time. And this is the forward propagation. Okay, the algorithm we discussed here, the forward propagation. So we first calculate A, which is the sum over Wij times Xi, sum over I. That means sum over all the input nodes, input neurons. Okay, and times the corresponding weight. Okay, so that's J. For it, this is for the J hidden node. Okay, so we do this sum. Okay, straightforward. Okay, given by this. Okay, this is the sum. Okay, and if J is not than 0, Xj equals G Aj. Okay, it is this one. Okay, Xj equals G Aj, and X0 is for the bias, it is equal to 1. Okay. And also this implements the CL, the sum over say WOJL times XJ, okay, WOJL, okay, times XJ, okay, this formula, and then the YL is equal to GCL, okay, the very straightforward, okay, and then we return the output, okay, in case we need to do the test. Okay. Actually, we return the pointer to the array that holds the output. Okay, so that's a pointer. And this is the backward propagation algorithm. Okay, backward. Again, it is straightforward implementation. So we have the delta, basically the delta J we mentioned, and delta O K. Okay, there's the delta L. Okay. So for the first part, we calculate the delta L. You see, delta L is this EL, the difference between the desired output and the predicted output. Okay, the output that is given by the MLP. Okay, and then we multiply this to the gradient of CL. Okay, so you can see that this is the straightforward implementation of these formulas. Okay, E equals the difference, and then delta OL, okay, is E times that. Okay, no tricks here. And then for delta J, okay, it's for the hidden layer. Okay, we do the same thing, delta J. So we have delta L times WO JL, okay, times G dash AJ, okay, GD AJ, okay, straightforward. Okay. And here we update the weights again according to these formulas. Right? Say WOJL, okay, WOJL, okay, is incremented by eta times delta L, okay, times XJ, straightforward implementation. Okay. And then we also update the weights input to hidden. Okay, Wij is incremented by eta, okay, times delta J, okay, times xi. Okay, so very straightforward. And get input data is to put the input data into this X, okay, the X array. Okay, so we get the data from the inputs we define here at the very beginning. Inputs ki. Okay, so X will point to so first this when k equals 0, it points to this set of data 1 0 0, and then we increment k. Then it points to 1 0 1, and then increment k again, it points to here and here. So that's to get the data from the inputs set. Okay, that's what this get input data does. Okay. Now this is the training. Okay, so the training, we do that for lump sample size. Okay, sorry. The lump samples is the number of different input sets. It is 4 here, and apples is the number of times we want to train the MLP. Okay, so we have this for loop. Okay, train it that many times, and for each time we have to go through all those samples, the 4 samples, the 4 input sets. Okay, so we get the data and put that in X. Okay, we first do the forward propagation and then the backward propagation. Okay. And also we let YD plus K times K, so they point to the appropriate desired output. Okay, so K is 1 here. So as K increases, so YD increases also. Okay, first it points to 0, and then next in the next K, next sample, it points to 1, and next it points to 1 and 0. Okay, so that's what this does. Okay, this does. Okay, and the backward, this function will do the updates of the weights. Okay, so we iterate through this and get the final set of weights. Okay, so print weights to print out the weights for reference. Okay, nothing special. And a destructor, and we have a classifier because the values that we deal with are doubles. Okay, so we classify that to be 0 and 1. That's our targets. Okay, if X is smaller than 0.2 and larger than negative 0.1, we return 0. That means that belongs to a 0. Okay, and this in this range, so 0.8 1.1 we classify as 1. Otherwise, we fail, we return negative 1. Okay, so this is training data for the exclusive OR gate. Okay, so this to be changed. XOR. Okay. And we use a learning rate of 0.5. Okay, say 4 sets of data. Okay, train for 10,000 times. Okay, this is for testing. After training, we try to say give the function, for function, and input X. Okay, basically from 0 0 to 0 1 1 0 1 1, and see if it would give us the correct result. Okay, so we call this function to do the test and then classify the output. Okay, and we also print out the actual output value obtained from the Perceptron. Okay, and for our reference, we also print out the weights. Okay, now let's try to execute the program again. Okay, so well, we get the same result. Let's clear this. Execute. Okay. So you can see that we get what we expect, okay, from this program. Okay, so we have a 0, x equals to 0 is 0, but the actual value of this value returned from the forward prediction is 0.02, so we classify as 0. And for this one, actually the actual output from the MLP is 0.98, and this is also 0.98, so it is classified as 1. And for this, it is 0.02, it is classified as 0. Okay, so this is the strict implementation of the MLP we discussed. Okay. Now, we can try other examples. Now, let's try another simple examples. Okay. Let's consider a binary full adder. Okay. So in a binary full adder, we have 3 input bits, okay, or we add 3 bits together, and we get a sum and a carry, okay, as C. Okay, so these are the results of the addition. Okay, so these are the 3 input bits x1, x2, x3. When we add 0 to 0 to 0, then we get a sum of 0 and a carry 0. Okay, and 0 plus 0 plus 1, we get a sum of 1 and carry 0. Okay, the same for this 0, 1, 0, we get 0, 1. And when we add 0 to 1 to 1, then we get a sum of 0. Okay, and a carry 1. And this we get 1, 0, 0, we get 0, 1, 1, 0, 1, we add 2 ones to we get a sum of 0 and a carry of 1. Okay, 1, 0, we get 1, 0, and when we add 1 and 1 and 1, we get a sum of 1, okay, and a carry of 1. Okay, so we can modify our MLP, okay, with 3 inputs now, okay, or N1 will be 4, okay, and 2 outputs, that means K equals 2, okay, so K equals 2, and we will use 4 hidden nodes, so M1 becomes 5. Okay. Now let's copy this program, CP MLP.cpp, okay, to MLP FA for full adder CPP. We just need to modify the input data and some parameters. The algorithm is still the same. Okay, so in this program, MLP FA.cpp, so we delete this old data and use the new one. Okay, so here the N1 becomes 4, M1 becomes 5, K is 2 outputs, and the number of samples is 8. Okay, and then this is still the same. Input samples data would be say 1, 0, 0, 0. So this is x0, x1, x2, x3, and so totally we have 8 of this. Okay. And for the target outputs or labels, okay, so again we have XS. So for each set we have two outputs. So it's 0, 0 correspond to these inputs, okay, and 0, 1 is for this, okay. This from this table, okay, and these are just random ways, okay, from input to hidden, okay, and now our N1 and M1 have been changed. This is the random ways from hidden to output, okay, WO. So the M1 and K have been changed. K is equal to 2 now. Okay. So all others are the same. We do not need to make any change. And maybe we just slightly modified the output format. Here we need to change it for the lump samples of 8, okay, still 10,000 times. And just slightly modify this. Okay, so again, to retest it using our inputs, okay, we make X points to our inputs and use the data to test, okay, our perceptron, sorry, our MLP. Okay. So this is the MLP for full adder. Now let's compile it, okay, and execute it. So again, you see that the test shows that the training was successful. So you have this input 0, 0, and then the outputs carry the sum, okay, correct, okay. 0, 0, 1 is 0, 1, 0, 1, 0, 0, 1, 0, 1, 1 is 1, 0, 1, 0, 0 is 0, 1, 1, 0, 1 is 1, 0, okay. The sum is 0, carry is 1, 1, 1, 0 is 1, 0, 1, 1, 1, okay. You get the sum to be 1 and carry to be 1, okay. And these are the actual outputs, okay, from the MLP, okay. But we classify them to 0 or 1, okay. So actually they are close to zeros, okay. And this is close to 1, okay, for this one, okay. And these are the ways, okay, just for your reference, okay. Okay, so we can see that the algorithm also works for 2 outputs, okay. And of course you can try that for other input data, okay. So this is what I want to talk about today, a very simple example of multi-layer perceptron and back propagation in C, C++. Okay. So if you think that this video is helpful to you, please give a like. Thank you for watching. Okay, see you next time.